Hi, welcome back. This is 3.1 on exponential functions and college algebra. So let's start out with just defining what they are. I'm going to give you some shape to your ideas. So exponential function, base b for boy. And what do they look like? It'll look like this. F of x equals b to some variable x. Okay. The b value has some restrictions. It needs to be greater than 0, and it also, we're not going to let it equal 1, because if it equaled 1, 1 to any power is just 1, so that would just be a horizontal line. Okay, so we don't let it equal 1. You probably could, if you let b be less than 0, you would have issues when you put like 1/2 in for x. So you'd get like imaginary numbers, and we want to avoid that. So that's why we're going to say let b be greater than 0. Okay. Okay, so the first kind of problem is just, can you put it into your calculator? And one thing I should note that, you know, we're used to, we are used to things like x to the 5th, right? We can handle that. It's like polynomial stuff, or maybe even x squared. This is kind of the reverse case. So what we have with x to the 5th and x squared, the base is variable, but the exponent is a constant. Now the base is a constant, but the exponent is variable. It's you know, it's a switch, right? Crisscross, right? Okay, so now we'll have things like 5 to the x or 2 to the x. Okay, so the base is constant, but the exponent is variable. Okay. Okay. So let's get in there. The first part is just, can you use your calculator to evaluate these things? And some of them can be kind of annoying, like this guy, 3 to the root 5, right? You get no problem figuring out like 3 squared, right? You could do that in your calculator, I bet. 3 squared, you can do that in your head, that's just 9. But something like 3 to the power of root 5, that's a bridge too far maybe for some of us. How would I type that in? Well, you have probably 2 different buttons on your calculator for exponents. You have this caret button, or you can have this, what is it, a y to the x button. It'll be one of those, okay? I'll show you how to do it for the caret button. So for the caret button, you'll press 3, then you'll press caret, then you could press, I think most calculators you could press the square root, and sometimes you need parentheses, sometimes not. Sometimes they put the parenthesis in there for you. If they put it in there for you, then you just type 5, but then you end up having to end the parenthesis, right? And then you go like that. And then, of course, push enter. Okay. I think that works for the TI-30XS. Let me look at my calculator and see if that's the spiel. 3 to the second square root. Yeah, my calculator, the TI-30X2S TI, which I don't recommend as a calculator, but it can get you through, you know, hard times when, like, my other calculator's dead. It's just not working anymore, so I have to use this calculator. Okay, so anyways, we type that in your calculator, push enter, you'll get about 11.66. Okay, so make sure you can evaluate these, because the first part we need to do is graphing using a table. And what we'll do is put a bunch of x values in the table and find the corresponding y values and then plot all the points. Okay, so let's take a look at that kind of problem. Graphing. We just want to figure out what's the basic shape of this thing. Okay, in the beginning, the best way to figure that out is just to do a table. Right. Okay, so I'll go x and, okay, so my example, something like g of x is 1 over 3 to the x. Okay, and I'm going to do a table here. I have my x and my y. And I'm going to go from -2, -1, 0, 1, 2, and plug those into this thing. So I have 1/3 to the -2nd power. It's the same as 3 to the 2nd power, which is the same as 9. Okay, so you have to kind of remember your exponent laws too, right? Above, let me just remind you, 1/3 to the -2 is the same as 1 to the -2 all over 3 to the -2. 1 to any power is 1 all over 3 to the -2. And then if you bring the 3 to the -2 to the numerator, you just have to change the exponent. Okay, so that'll just be 3 squared, which is 9. Let's do this guy. Okay, it's the same kind of spiel, -1. One thing you could do, another kind of trick is if you have a negative exponent on the outside of a fraction like that, you could just flip the inside, okay, and then change the sign of the exponent. And then it's just, 3 divided by 1 is the same as 3. And then anything to the first power, you just get that anything right back. So it's just 3. 3 to the first power is 3. 1/3 to the 0. Anything to the 0 power besides 0 is 1. Okay, so this will be 1. 1/3 to the 1 is just 1/3. 1/3 squared. So you can distribute the exponent if you want, or you could just go 1/3 times 1/3. That's the same thing as well. Anyways, you get 1/9. Okay, so we want to graph the sky in the xy plane. We need plenty of y space. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going over 1, 2, 1, 2, 2, -1, 1, 2. So at -2, it's at 9. At -1, it's at 1, 2, 3. At 0, it's 1. At 1, it's 1/3. And then it gets even lower at 1/9. So it looks like a ramp. Okay. And it's going in this direction. I missed my dots, but hopefully I can cheat a little bit there. Just make the dots really big. And that thing right there is an exponential function. G of x is, Okay, so what are the characteristics of these things? Do they all look the same? Well, yeah, pretty much. So we're going to through the characteristics. Okay, so first off, the domain and range issue. The domain is just like the polynomial. You can literally use any x value. Okay, so it's -infinity to infinity. The range is a little different. The range is always going to go from 0 to infinity. Okay. And if you look at the graph above and you did like the trash compactor thing from before, so here's the sides of the trash compactor. And if they smush the graph onto the y-axis, you would have kind of blood and guts all along here, but not including 0. Okay, so you get really close to 0, but not all the way down. There's nothing you could put into the exponent of g of x. So 1/3 to, just think about it, what power can you raise 1/3 to give you 0? And it just never happens. Okay? So 0 is not included. What else? X and y intercepts. So we're just looking at like the same characteristics that we find for graphing rational functions or polynomials. For the x-intercept, there is none, right? Because the x will never be 0. So the x-intercept, there's none. For the y-intercept, that's where x is equal to 0, so that'll always be 1, right? So if you have your exponential function being b to some power x, and you plug in 0 for x, our rule for raising something to 0 power is it turns it into 1. So that tells us our y-intercept is going to be 0, 1. Okay. What else? The basic shape. There's 2 versions, just like with parabolas, there's kind of 2 versions. There's what I would call exponential growth, which looks like this, and then exponential decay, which looks like this. Okay. All right. The first case you could tell by the b value. This will be the case where b is greater than 1. And the other case is when b is in between 0 and 1. So if you look at the above graph, this example, that was the exponential decay kind. And if you look at the base, 1/3, that's less than 1. So that's the second case here. So b will be less than 1 but greater than 0. Okay. Okay. Let's see what else we got going here. These things are invertible. Okay, y equals b to the x is 1 to 1. It passes the horizontal line test and thus invertible. So somewhere out there exists an inverse function, and we will be working with that thing. We will give it a name eventually. And thus is invertible. What else? It has an asymptote, although you can't see it. Y equals 0 is a horizontal asymptote. Okay, so y equals 0 is just the x-axis. So you don't see it, but it's there. I'll put it in yellow or something. I'm not giving you yellow. There you go. There it is. And for both of them. Okay. Okay. Other than point plotting, you can always use shifting once you have the picture in mind of what these guys look like. You can use transformations to create new graphs. So using transformations. You just kind of have to remember how they work. So for example, let's look at this guy. We have 2 goals in mind. We need to graph 3 to the x, and then we also want to graph, let's call it something else. Let's not call it f again. Let's call it g of x, and that will be 3 to the x minus 1. Okay, so I'll get a picture of f of x, and then I'll use transformations to get g of x. Okay, so here's x, here's y, -2, -1, 0, 1, 2. Okay, so I have 3 to the -2. I can rewrite that as 1 over 3 squared, which is 1 over 9. Then I'll have 3 to the -1, same as 1 over 3 to the +1, which is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. Yeah, okay. So let's graph that first guy. I'll put him in white. Okay. So I have -2, whoops. Let's erase that. Where am I? -2 1/9 is down here, -2 1/3, a little bit higher, and then 0 1 of course, and then 1 3, and 2 9. So it's an exponential growth curve. Okay, and then this other guy, what does it do? That shifts it to the right by 1. Okay, so if you have g of x equaling 3 to the x and then -1, this would be a shift down. But if the -1 is in the exponent, this is a shift right by 1. Okay. Okay, so I take each one of these dots and I'm going to shift it over. I'll do this in red, I guess. I'll shift it over by 1. So I need another tick mark as well. So this will go over to here. This point will go over to here. This point will go to here. This point will go to about right here. And this will go to here. And then I'll have my new graph. Okay. Okay. So The software will probably ask you for domain and range and stuff like that, so let's go ahead and talk about that as well. The domain of f, of course, is negative infinity to infinity, and the range of f, of course, is 0 to infinity. And it's the same for the domain and range of g. Okay. You may recognize that this, you may realize that this thing is just a rotated version of this example up here. So how is that? How does f of x equaling 3 to the x relate to this other guy, g of x, equaling 1/3 x, 1/3 to the x? Well, the trick is you can rewrite the second function, right? You can rewrite g of x equals 3 to the negative 1 x, and then you could rewrite this g of x as 3 to the negative x. Okay, which just means that we're doing a y-axis rotation. So to go from here to the other one, you do a y-axis rotate. Okay. In other words, we began with this thing, y equals 3 to the x, and then after you rotate, you're going to end up with the exponential decay curve, okay, this thing. Okay, so that's how those two are related. Let's look at one more. So another example, f of x equals 2 to the x, and then g of x equals 2 to the x plus 1. Okay. All right, so again, I'm going to do a little table for f of x. So -2, -1, 0, 1, 2. 2 to the negative 2 is 1/4, or 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1 over 2 to the 1, which is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. Okay, so I'll graph those. I'll do those in white. So I have -2, 1/4, -1, 1/2, 0, 1, 1, 1, 2, 2, and 4. So another exponential growth curve, going like this. Okay. And if you add a 1 on the outside, what's that going to do? That's going to shift it up by 1. So let's put that in yellow. So everything goes up 1. Whoops, that last point, I must have misdrawn that. That would be at 2, 4, which is right here. Okay, sorry about that. Ugh. Trying to draw that as well as I can. Okay, and then I'll do the other one in yellow. So I have to shift all these points up by 1. And in doing so, you actually move the asymptote as well. Okay, so in the previous problem, that wasn't an issue. But here, if you move up by 1, you'll have a new asymptote. It's like the asymptote goes along for the ride. Okay. So I'm drawing the new asymptote in blue. The old asymptote was on the x-axis. I'll put that in red. Okay. So this is the old asymptote. And the blue guy is the new asymptote. Okay, so as you shift up the actual picture, you also have to shift up the asymptote. Okay. There's one base that comes up in a lot of applications in math modeling and in finance, and that is the natural base e. It's a number like pi. Okay. And e is approximately 2.718281827, just like pi. You know, pi is 3.14159, blah, blah, blah. You can find it on your calculator. There should be a little button. So on the calculator, I'm looking for it. if you have the TI 80 or TI 30X like I do, it's above the LN button. Okay, so there's an LN button, and then right above it in blue, there's an E to the X. Okay, so you're going to need to hit the second key and then the LN, and then you'll get the E to the X. Okay, so you should try to evaluate E cubed just to make sure you can do it in your calculator before you get too deep into the business. Okay, so we have 20.09. Okay, just one second. Okay, let's take a look at some examples. So like I was saying, one example where this will pop up is in math modeling, especially in dealing with biology, and you're looking at populations of animals, or you're looking at I don't know, population of fruit flies, something like that, even population of humans and disease, you can model using mathematics. So an example, they give you this function, which looks pretty crazy. F of x is 1145 e to the 0.0325x, and f of x represents the number of gray wolves, and then x is the number of years after 1978. Okay, so they want to know, first off, what is, I think this is the only part we'll look at, what is the population in 2017? Okay, so first we have to figure out how many years after 1978 that is, and that won't be so hard. I can just take 217 and subtract away 1978, and of course you get so 39. Okay, and then we take the 39 and plug it into our formula for wolves. Okay. So this, you have to be able to put this into your calculator. 325 times 39. So that's 0.0325 times 39. And if you do it, you will get about 4,067 wolves. Okay, so biology, certainly, it's going to come up there. Where else? Well, finances, interest. People have been doing banking since forever. Okay, it's just literally they find stone tablets from 500 BC that have investments written on them and stuff like that. Okay. This number E comes up when you're dealing with compound interest. Okay, so we need to work with this and define some things. We have P for principal. That's just the money you either put into an account or a loan you take out of a bank. R is going to be the rate, and this is a rate per year. And in the equation, we use it as a decimal. In equation. Okay. And then A is going to be a future value or accumulated value. Okay, so the accumulated value is going to be the principal plus the interest. Okay, so interest, maybe I should say, I is interest. Interest is just usually principal times rate times time, right? If we just want 1 year, though, how much money am I going to have in my account after 1 year? If I put P in there initially, I'll have P plus the interest over 1 year, so P times R times 1, right? Okay, we can simplify this and have P times 1 plus R. And then we'll do this over a number of years and kind of look for a formula. And a formula does kind of rear its ugly head. Notice, we'll look at the year and then the accumulated amount. Okay, so in year 0, let's say I'm putting P dollars into an account. Okay. So after 1 year, I'll have the original amount plus the interest on that original amount, P times R. I'm going to rewrite it as P times 1 plus R. Okay. After 2 years, I'll have the amount from last year in the account plus the interest on that. So that will be P times 1 plus R times another R. Okay. And then we can factor out. We can factor out a P times 1 plus R. And the leftover, we have 1 and then plus R. So you see, if I distributed this, I would get back to where I started. I would get back to here. Okay. So hopefully that convinces you. And you could rewrite that as P times 1 plus R times 1 plus R. Or P times 1 plus R squared. Like that. Okay. Okay, so what about year 3? And this is called an iteration method. We are looking for our formula by just looking at patterns. So that's one of the cool things about math. You do get to study patterns. Okay. So year 3, we get the stuff from year 2. So P times 1 plus R squared, that's the amount from year 2. And then plus interest of this stuff. So you just multiply that by R. And again, you can factor out now P times 1 plus R squared. And you're left with 1 plus R. And then you can multiply that together, the 1 plus R squared times the 1 plus R to the first power. Just add the exponents. And you get P times 1 plus R cubed. So after 1 year, you get P times 1 plus R. After 2 years, you get P times 1 plus R squared. After 3 years, you get P times 1 plus R cubed. So what do you think you get after 5 years? Huh? Well, you're going to get P times 1 plus R to the 5th. So you have a formula. You have a general formula. After 2 years, we have accumulated A equals P times 1 plus R to the tth power. Okay. Okay. Of course, when you go to the bank, you're probably not going to have yearly interest, right? You'll compound n times a year. So if you take that into account, and you could go through the same kind of iteration technique, supposing n compounding periods per year, we'll have the following formula, which I'm not going to derive. Okay, I'm just going to give it to you. We have this thing. And then furthermore, if we let n go to infinity, in other words, we compound basically every nanosecond. If we let n go to infinity, we get the following formula, which has the number e in it. Believe it or not, that number e just kind of pops up. Okay, it's a little like the number pi in that if you're trying to get the area of a circle, you could approximate it with a bunch of little triangles, right? You could put like a triangle here, a triangle there, triangle here, triangle here, triangle here, triangle here, triangle here, triangle here. And the area of the triangles will be a pretty good approximation. Then you start throwing in more and more triangles, and that's kind of like letting n go to infinity, letting the number of compounding periods go to infinity. And what's going to happen in the end, if you get enough triangles in there, if you let the number of triangles go to infinity, is you're going to get kind of the exact area. And that area, of course, will have that number pi in it. Okay, so it's just like that, and you study that kind of process in calculus. Okay, it's called a limit. So you spend a lot of time in those classes worrying about that issue. Okay? But anyways, like I said, it's just like the number pi, and it comes up in this kind of process where you're, okay. Let's look at a homework type problem. So they're telling us our principal is $10,000. Our rate of interest is 0.08, and we have a time of 5 years. I want to know how much money will I have if it's compounded quarterly. Okay, so let me rewrite my formula just for a reference. A equals P times 1 plus R over N to the NT. And then the other one, A equals PE to the RT. Okay. Okay, so let's scroll up there. Quarterly compounding just basically means you're compounding 4 times a year. So N is 4. Okay. So the future value A will be 10,000 times 1 plus R, 0.08, all over N, which is 4, raised to the 4 times T, which is 5, so 20. And then I need to put that in my calculator. If you do so, you will get 14859.47. Okay, B, continuous compounding. And this is where we just use the other formula. So A equals PE to the RT, which in this case, if you do a substitution for P and all that, it'll be 10,000 E to the 0.08 times 5. Okay? And if you play it in your calculator, you'll get 14918.25, which isn't that far off from the quarterly compounding. But if you think about it in terms of like the circle where you're doing approximations, so you approximate it with 4 triangles, you're not that far off from the actual area of the circle, right? You're just missing these little pieces. And that's kind of the same spiel here. The quarterly compounding, you know, it's $100 off, but it's not that far off. It's just these little slices I'm really missing out on, okay? Okay, so it's fascinating stuff. A great job to get is in banking because people need banks, right? I don't see the banks, well, maybe they will go out of business someday, but not in my lifetime, I bet, okay? Okay, so good job. A good job to get is in banking or in insurance. My gosh, I would love to get a job in insurance, right? With all the Progressive insurance and all that stuff. Okay, so that'll do it for this section. Thanks for watching, and we will see you next time.